if you think about it, we now know how to do derivatives of just about everything. There's just one last corner to clean up, and that is we don't know what happens to the derivative of a function raised to a function. If this is a constant, we have the exponentiation formula. We know the derivative of a to the g of x is a to the g of x times the natural log of a times the derivative of g of x. We know that the derivative of a function raised to a constant is simply n times g of x to the n minus 1 times g prime of x, using the chain rule. But we don't know what happens when we have functions in the base and the exponent. To explore that, let's take an example. What would we find for the derivative with respect to x of, well, let's say, how about sine of x raised to the x squared power? Okay, because this is not a constant, we can't use the powers rule. Because this is not a constant, we can't use the change of base formula and the derivative of an exponential function. What we're going to do is give this thing a name. I'm going to let sine of x to the x squared, I'm going to call that thing, oh, I don't know, L. And then we're going to take the natural log of both sides. The natural log of the sine of x to the x squared is the natural log of L. L was probably a bad choice. Now we'll use the properties of logarithms. X squared times the natural log of the sine of x is the natural log of L. And now we'll take the derivative of everything. Call this L of x, because it's a function. The derivative here, we've got a product rule. 2x times the natural log of the sine of x. And again, we have to be careful because it's only defined when the sign is positive. 2x times the natural log of the sine of x times the derivative, or plus x squared times the derivative of the natural log of sine of x, which is 1 over sine of x times the derivative of sine of x, which is cosine of x. And that's equal to the derivative of the natural log of L of x. We have to use the chain rule on this side as well. When we use the chain rule on this side, we get 1 over L of x times L prime of x. And that's, of course, what we're looking for. We want to know what L prime of x is, because we want the derivative of sine of x to the x squared. So that's the thing we want to find. Okay, well, we've got this mess. Let's rewrite it. This is 2x natural log of sine of x plus x squared cosine x over sine of x, and that's equal to 1 over L of x times L prime of x. Let's multiply both sides by L of x, and then we get L of x times 2x natural log sine of x plus x squared, and if we wanted to, we could say cosine over sine is cotangent. Well, we don't want this left in terms of L of x, so we will say L of x was sine of x to the x squared, our original function up here. So this is sine of x to the x squared times 2x natural log sine of x plus x squared times the cotangent of x. This is an example of what's called logarithmic differentiation. We give this function, some people would call that the letter y. We let y be the function. We take the log of both sides, then take the derivative. Remember to apply the chain rule to both sides and the product rule over here. And finally, at the end, multiply back by original function y, which was sine of x to the x squared. If you want to, you can remember this as a formula. Most people remember it as a process. What would it look like as a formula? Let's just derive it once with the f of x to the g of x idea. We would let y equal f of x to the g of x. Then we'd take the natural log of both sides as an operator. The natural log of y is g of x times the natural log of f of x. Now we take the derivative of the entire thing. That's the derivative operator applied to everything. And we get 1 over y times dy dx. Over here, we take the derivative and use the product rule. That's g prime of x, natural log f of x, plus g of x times the derivative of the natural log of f of x, which is 1 over f of x times f prime of x. Multiplying back by y, and if you want to, you could put the g prime in and do all kinds of other fun stuff, but none of it really matters. Dy dx is equal to y, which is f of x to the g of x, times g prime log f plus g over f prime. Now, that's even worse to memorize than the quotient rule and is used far, far, far less often. So usually people, instead of memorizing this formula and plugging values in, they simply directly reprove it, rederive it for every special case. And this again is the derivative of f of x to the g of x. Okay, let's take one example that kind of points this all out at once. What would the derivative of the following function be? Let's call it x to the pi plus pi to the x plus x to the x plus pi to the pi. The reason I do this is so we remember what is a variable and what is a constant. Pi is a number. It's 3.14. It's a constant. So the derivative of x to the pi, and now we never proved it for irrationals, but it turns out to also be true for irrationals, is pi times x to the pi minus 1. Similarly, the derivative of pi to the x, this time we have an exponential function. Pi is the base, x is the exponent, so using the change of base formula, now we know that this is pi to the x times the natural log of pi. So notice the difference. Constant as an exponent, constant as a base. Here, where we have x to the x, we better do a little playing around and use our logarithmic differentiation. Plugging that into the formula, we'd have x to the x. And again, you're probably better off doing it by hand, but I'm just going to plug it into this formula. Times the derivative of x, which is 1, times the natural log of x, plus x over x times the derivative of x, which is 1. And then, what's the derivative of pi to the pi? Pi is a number, pi is a number. 3 cubed is about 27. This is probably a little under 30 or something, but the derivative of a constant is 0. So this gives you every possible variation you can have relating x's and constants in the base or the exponent. If you understand this example completely, then you have a pretty good understanding of the difference between power functions, exponential functions, functions raised to functions, and constants. So bear this one in mind when you're thinking about derivatives, exponents, bases, that variables, constants, that kind of thing.